Okay, howdy Ags. We are back for another episode of Exercise Biomechanics. Today, it's all about stress. Hope you're not feeling too much. So we're going to talk about stress, strain, material or mechanical properties, and what that has to do with connective tissues and skeletal muscle. So we've mentioned before, these mechanical or material properties are basically the health of our connective tissues, bones, tendons, ligaments, cartilage. That's what prevents them from getting injured. If we overcome their strength and stiffness and energy absorption or toughness, then a fracture or a tear or a sprain can occur, and lots of bad things can happen. So today we're going to start by really defining mechanical stress. So if I think about pressure as like the force being exerted on the surface of a material. So like when your shoe and foot lands on the ground, there is a certain amount of pressure that's being exerted. That's the force being produced, the ground reaction force, divided by the contact area or cross-sectional area. So if you're a midfoot striker, you got a lot of the shoe that's landing, and that, of course, reduces the pressure. But what about the stuff on the inside? Like inside the ankle or inside a critical bone, like here's the femur. So the stress, if pressure is what's felt on the outside, stress is basically what's felt on the inside. So the way we quantify this is the loading divided by the cross-sectional area, basically how thick something is. So pressure is what's felt on the inside. It's the response, we think, on the inside. And then pressure is what we feel on the outside or on the surface of a material. So with that in mind, remember there were 5 different types of loads that we talked about last time: compression, bending, tension, torsion, and shear. That means that there are 5 different types of mechanical stresses. There's compression or squeezing. There's bending, there's tension. So that might occur, for example, when the gluteus medius and gluteus maximus are tugging on the greater trochanter of the femur. There's torsion or twisting. And finally, there's shear stress, chopping or rubbing type of stress. Bones are weakest against shear type force. So a typical femur or tibia can take over 1 ton of compressive force before it breaks, but only about 500 to 600 pounds of shear force. So a lot of times when you have a fracture in a leg due to a football tackle or soccer or basketball, it's often a combination where there's some compression, but there's a big shear force, especially if you end up with something like a compound fracture. So again, for every single type of load, which is a force that causes a deformation or change in shape of an object, there is a type of mechanical stress: compressive, bending, tension, torsion, and shear. So let me click on the right thing so I can advance. There we go. So mathematically, stress, I'm going to have to fix this on the run. Let's see if I can do that. Hold on. Okay, sorry, we're back. I've been tweaking the slides a little bit, and there was an issue regarding font, etc. So stress, again, is basically the force being exerted divided by the cross-sectional area, if you will. So the units in the English and the metric system are units of force divided by units of area. So, but remember, it's not the same area that we saw for pressure, because that's the force being exerted on the surface. So it could be, for example, you're blowing up a tire or a basketball, and the pressure being exerted by the air molecules are on the inside surface of the tire as well as the basketball. So in the case of stress, it's actually the force being exerted inside the material, inside the bone, inside the tendon, the ligament, cartilage, concrete, steel, bone, what have you. Okay, so it's force divided by cross-sectional area. In the English system, it's pounds per square foot, or of course, square inch, I'm sorry. In the metric system, it's newtons per meter squared. Sometimes when we're looking at biological tissues, we don't really use the standard standard units. So for bone, for example, we might use meganewtons per meter squared. For skeletal muscle, stress inside a skeletal muscle is usually expressed as newtons per centimeter squared. So you sometimes see non-standard units when it comes to tissue biomechanics. So that's okay, we'll deal with it. So one of the reasons that we focus on mechanical stress and equating the force per cross-sectional area is so that we can talk about the quality of the material, what it's made of, how good is this bone, is it dense enough, is it strong enough. So what mechanical stress allows us to do is to be able to fairly compare bones from like a 100-pound person with a 200-pound person. It's not fair that someone's bigger. You've got to look at the quality of the material. So it's like comparing, let's say, a small piece of oak with a big piece of oak. The quality of the oak is dense. It's about the same. It's about the same stiffness and strength per cross-sectional area. One's just bigger than the other. But the material itself and the quality of the material is the same. So mechanical stress, mechanical strain, and when we get to material properties, we're often interested in the quality, how good that is for our body. So here we go. Again, it means for every different type of load, we got a type of mechanical stress, like tension, shear that we might see if someone is doing like a knee flexion exercise, or especially like a squat exercise where the femur can induce some shear forces on top of the tibia. This is a reminder that the human spine can deal with compressive stress, downward stress, but also torsion, because those are the types of forces or loads that they see the most. Your body weight and also moving, twisting around, etc. If we imagine a cat or a dog, turn our head sideways or turn the slide sideways, they actually have to deal with bending forces and shear forces more than we do. So their spines are adapted to that. In fact, the thickness in the cervical region isn't that much different than the lumbar region. There's a little bit more loading in the lumbar region than the cervical region, but the size of the vertebrae are much closer together than it is for a human. So we're going to do a little problem with mechanical stress. Let's say Sarah has a body mass of 62 kilograms. She's performing a military press with 200 newtons of weight. Her fifth lumbar vertebrae down there is 30 square centimeters in cross-sectional area. Her fifth lumbar vertebrae supports about 40% of her weight. So what's the total compressive stress on the fifth lumbar vertebrae? That's the last vertebrae before you get to the coccyx. So the mass is 62 kilograms for Sarah. That's her body mass. She's going to support 40% of that. The weight that she's lifting is 200 newtons. 100% of that weight has to be supported by the fifth lumbar vertebrae, not just 40%, all of it. So that's going to be a significant amount of stress when we add that on. The fifth lumbar vertebrae has a cross-sectional area of 30 square centimeters. So we're going to find mechanical stress. We use sigma to describe that. Here's Sarah again. So the stress is equal to force divided by, again, cross-sectional area, and where force is equal to mass times acceleration due to gravity. So we've got 62 kilograms times 9.81 meters per second squared, and we crunch those numbers out. That's 608.22 newtons. We've got 40% of her body weight times 608.22 newtons, plus the 200 newton weight that she's actually lifting, and that gives us 443.29 newtons. That's the force. Now we have to do is calculate the stress, which is the force divided by the cross-sectional area. So that's 443.29 newtons divided by 30 square centimeters, and that gives me 14.78 newtons per centimeter squared. So that's the amount of stress that that fifth lumbar vertebrae and the vertebral disc will have to deal with, compressive stress. The next thing we want to talk about is a very important person in terms of adaptation, Sir Hans Selye, who lived from 1907 to 1982, was an endocrinologist and physician. He's widely known for something called the general adaptation syndrome. And this is the way we think about bodies and animals and physiology adapting to things. And whether it's mechanical stress or physical stress or chemical stress or metabolic stress or emotional stress. When our body's trying to deal with that, we have three stages: an immediate response. So if someone starts running and jogging, for example, there's an increase in blood flow. As the heart starts to pump more blood, we get an increase in stroke volume and an increase in heart rate. That combines to increase the amount of blood, blood flow that is pumped through the muscles and the heart, etc. So an increase in blood flow is one of the responses. There's also an opening of arterioles in skeletal muscle and the heart, trying to feed them. We also see an increase in naturally oxygen consumption and oxygen demand in the tissues. So there's that immediate response. If it's a hot day and it's starting to get warm, you may start sweating as you start to exercise, and that's an immediate response to try to cool the body. Then we can have adaptation over time. We can have adaptations to heat. As you know, in fact, some of the exercise adaptations that are really important biochemically are actually adaptations to heat as much as they are adaptations to exercise. It's not quite 50-50, but both turn out to be really important. If we're weightlifting, for example, the resistance could be an increase in muscle cross-sectional area. But not only muscle, it could be bone or tendon or ligament or cartilage. They all respond to exercise training over time by naturally increasing their mass and often their cross-sectional area to try to deal with the enhanced stress and force. So that way, that mechanical stress and strain come down into what they would think of as a homeostatic level that they can deal with. Exhaustion or failure happens when there's too much stress. So this could be a compound fracture of the tibia. It could be a tear of the anterior cruciate ligament. It could be a partial tear or a strain of the hamstrings muscle. So we think of this as kind of a continuum where there's really super high stress that can cause an injury. It could be the magnitude of the stress, or it could be the frequency, or even the type. You need a certain amount of mechanical stress just to maintain current status. Too low causes atrophy of muscles, tendons, ligaments, cartilage, and muscle and bone. Each one is going to atrophy at its own rate. It may surprise you to learn that cartilage actually atrophies the fastest. Skeletal muscle is kind of next, and then bones, tendons, and ligaments. In terms of increasing mass, hypertrophy, that happens when there's an increase in mechanical stress, but it's in the Goldilocks zone. Not too little, not too much, getting it just right. So the adaptation is an increase in mass, cross-sectional area, density if it's a bone. So what's important is the magnitude, the intensity of the stress, the type of stress. For a ligament, for example, compared with a tendon, you see more shear and torsion. So when there's an ACL reconstruction and you have a new ACL, which is basically the middle third of the patella tendon or semimembranosus or semitendinosus tendon, what you tend to get is a transformation over time. The cells for tendons and ligaments are exactly the same. They're fibroblasts. But the fibroblast in the tendon graft adapts to the fact that, unlike tendons, which see almost exclusively tension or pulling forces, a ligament can see some torsion, can see some bending, can see some shear forces. So its collagen fibers are laid down a bit differently. And that means that that graft has to adapt to this new mechanical environment over time. And it does do that over the first 6 to 9 months or so. So really kind of cool and exciting. If there's, again, too much mechanical stress, can cause a broken back, a fracture to the neck of the femur. That's what we call a broken hip. That's something we obviously want to avoid at all costs, especially as we get older. With mechanical stress, you do have to watch out sometimes after we get past the coronavirus. Hopefully, we won't have much of a severe season this year. Hurricanes, tropical systems will stay away. If one does come, make sure you put your plywood on the outside instead of the inside. I heard the owner of Lupo's wanted to prevent glass from getting on the inside, so they put the plywood on the inside. But you're supposed to put the plywood on the outside. So what that does is if an object, a flying object hits it, the wood can actually absorb the shock and reduce that impact force, partly because it actually deforms and changes its shape and increases delta T. So it's hard to get around that impulse equation. Okay. So adaptations, again, happen. Sirhan-Selye's general adaptation syndrome, and adaptations are how basically species survive, individuals survive, how tissues adapt so they don't get injured or re-injured. So one of the cool adaptations in the human spine is in the first 2 years of life. So as a baby, babies are mostly supine, lying around, and after a while, most of them can sit up by 6 months. Some can stand, even move around and bounce around by 9 months. Many can walk by 12 or 13 months. It doesn't really seem to matter as far as we know if you're just anywhere in between the 9 to 15 month range in terms of when you started to walk. It's usually not that big a deal. We're not even sure if it means anything, and hardly seems to run in families. I walk kind of early, but my kids walk later. There is some argument that children who crawl for longer develop a larger brain, and maybe that was the case. I think my kids actually wouldn't walk until they could run. So that was big trouble for us because we had to put things away really quickly. So as soon as they could stand and they could take a step and say, yeah, that's cool. But it's like, I can crawl faster than that, so this doesn't seem very efficient. So they could run just about the same time they could walk, or decided to walk, I think, in this case. So in the first 2 years, what we see is an increased load that the lumbar and the lower thoracic region has to bear. And because of that increase in force, the adaptation is an increase in cross-sectional area. So if stress is equal to force divided by cross-sectional area, if the load goes up, or if for stress is equal to the force divided by the cross-sectional area, if the force goes up, then the cross-sectional area is the adaptation to try to get back to a normal stress or strain level. So we need some mechanical stress in order for tissues to actually maintain normal function, Excuse me. Hold on a second. Okay, sorry, a little tickle in my throat. As I was saying, you need some mechanical stress. You need things in the Goldilocks zone just to maintain current strength and structural integrity of connective tissues and skeletal muscle. If there's a change in mechanical stress, there's, not surprisingly, an adaptation. So if there's an increase in stress, not surprisingly, your body adapts by increasing protein synthesis in tendons, ligaments, cartilage, skeletal muscle, and then increasing its mass. If it's a bone, it could increase its density, particularly in adults. During space flight, what we see is, of course, a reduction in mechanical stress as we're in a microgravity or a weightless environment. So in the numerator, there's hardly anything. So that means that the cross-sectional area, well, the body doesn't really need to maintain that. It's expensive to keep up tendons, ligaments, muscles, and bones. It costs a lot of ATP, costs a lot of energy. And it probably means someone's bedridden or sick, in which case you actually need more protein and more amino acids. So that's sort of the body's logic in terms of unloading, whether it's casting or space flight or someone is bedridden. We lose muscle mass and cartilage, bone mass and tendon and ligament mass as well. And it can happen pretty rapidly. Unfortunately, the increase in mass and cross-sectional area with weightlifting, with exercise, is a bit slower than what happens with space flight and with casting when we actually lose mass. But pretty cool changes nonetheless. So, of course, NASA and the astronauts are really interested in trying to reduce the amount of bone loss, skeletal muscle mass, and strength loss in space flight, as well as their tendons and ligaments and cartilage. In fact, the changes in cartilage are really surprising. They're a little weird because in the spine, for example, the vertebral discs actually swell and you actually gain height a couple of inches in spaceflight. Unfortunately, you don't keep it when you come back to Earth, and the cartilage that's there tends to suffer because it's had a loss of a type of protein that we call proteoglycans. It's a special type of protein with a lot of carbohydrate and some protein, more carbohydrate than protein. When mechanical stress leads to an injury, it's either because the magnitude's too high, either in compressive stress, or it's the wrong type. Like, for example, 500 pounds of compressive stress, no big deal. Femur and the tibia are going to see that when someone's maybe running, playing tennis, playing volleyball or basketball. But if they see large shear force, then that's big trouble, because only 500 pounds, 600 pounds can cause a fracture. If the frequency is really high, the magnitude, the intensity doesn't have to be very high to cause a fracture. So we would call this, if it's a bone fracture, like a stress fracture. Or if it's an injury to a muscle, it's actually delayed onset muscle soreness. For a tendon, it would be tendinitis. For some ligament structures, like you can get plantar fasciitis, which is, again, kind of a ligament material because it's going from bone to bone on the bottom side of the arch of the foot. You can have a partial or a complete fracture, and that really depends upon how much force is being exerted. The age of the person makes a difference, because the amount of ductility, that's the opposite of brittleness, is much higher in the bone of a young person than it is in a young adult or someone who's older, someone who's senior. So we have two types of basic injuries to muscles and connective tissue. The first one that's traumatic injury. So that's caused by a very large load, a very large amount of stress that can cause a significant fracture, significant tear of a ligament or tendon, or even skeletal muscle. Someone could be on a balance beam, for example, and fall off. They could be, let's say, skiing, and they fall over the boot, and you get this compound fracture that's caused by a combination of shear and bending and compression. So it produces what we call macro trauma, very large magnitude, unusual types of stress, and that usually means shear type of stress, combination loads, and then it's really low repetition, once or twice. You don't need basically a lot of stressors. So falling off a bicycle, car accident, for example, tackle in football, those are all examples of traumatic injuries. So again, bone fractures, tears of a tendon, ligament, sprain of a ligament. Material fatigue injuries. This may not be quite as familiar to you. So it means that if you take, let's say, and I'm not going to do this, if I take a little hammer, and I've got my finger here, hammer and bang on this drywall, I'm not going to do that because my wife would not be happy with me, I can probably cause over time that drywall to start to break down. And that's because of repeated stress. If I just hit it once, everything's cool. I didn't produce a lot of force. But if I kept doing that, that's Trixie sleeping below me, by the way. I was starting to make some noise. If I keep hitting the wall, then it's going to start to break down. If you've seen The Shawshank Redemption, you know, with a rock hammer and 30 years and not much else to do, you can break out of a prison if it has the right type of wall. I think it was a shale wall, which is actually made of seashells. So it's accumulation of microtrauma. Does this happen in the body? Absolutely. Delayed onset muscle soreness is probably the most common type of microtrauma or material fatigue injury. These are overuse injuries where there's a lot of repetition, but the loading isn't enough to cause like a muscle tear. Or if it's a bone, it causes a stress fracture or a stress reaction, which is an inflammation of the bone. A stress fracture is basically a microfracture, where some small microfractures have accumulated over time. Shin splints are another really good example. Tendonitis is a great example. Some tendon ruptures are caused by accumulated microtrauma that occur over time. Chondromalacia in the knee, and as we mentioned, delayed onset muscle soreness is the most common type of material fatigue injury. So again, material fatigue injuries occur when there's a modest amount of mechanical stress in terms of intensity or magnitude, but they're repeated over and over again. So what's happening is that the body's not getting enough of a chance to repair itself. So there's a process called remodeling. It's going on in your bones and tendons and ligaments all the time, where you're laying down new protein and taking away the old protein. So this is a constant phenomenon that's going on. And one of the ways we can characterize this and even quantify this is to look at the load magnitude or stress on the y-axis and the frequency of loading on the x-axis. So what it means is when there's a very little frequency, just boom, something happens and it's a very large stress, you can get a traumatic injury, like fracturing the wrist, for example. But if you have repeated stress, this can even happen in skeletal muscle when you go bowling, for example. Or even golf, if you go out to the range. Actually, now that we're talking about and trying to honor, I guess, some social distancing, going to the golf range isn't bad as long as your area has not been locked down. Brazos County just got locked down yesterday, so we're supposed to stay at home unless we need to go get some groceries or drugs from the pharmacy, etc. So we're kind of staying in place. But it's actually a good idea to go outside because you have sunlight. Actually, the virus doesn't like sunlight, believe it or not, because of the ultraviolet light. And heat may or may not help. So the virus has basically a covering, a lipid bilayer, which is like a cell membrane. So that's why it's susceptible to soap, because soap dissolves it, believe it or not. And alcohol will dissolve that membrane and inactivate the virus. Ammonia products will do that as well. As cleaning products, disinfectants. So that would be like Lysol, for example. Hydrogen peroxide can also do it as well. So a lot of the disinfectants, cleaning products, what they do is they inactivate or damage through lipid peroxidation or another mechanism the cell or the membrane that's around the virus, which is embedded with some proteins. And then there's RNA that replicates. It's basically like a Xerox, a cloning machine. So, okay. So actually being outside is okay, as long as you're not around a lot of other people. Okay, so back to our slide. Again, traumatic injury, we have a low frequency of loading, really high load magnitude or intensity or high stress. Material fatigue, again, it's like delayed onset muscle soreness or like a stress fracture or tendonitis. And they happen with just a moderate amount of loading, but high frequency of loading, high frequency of loading. Oh, we're at the end. That's okay, so that's the end of this set of slides. The next thing we're going to do is we're going to talk about mechanical strain and then put it together with stress strain curves, which are going to tell us about material properties of tendons, ligaments, bones, etc. I'll show you how to read these curves. We're going to use them when we make comparisons, basically old bone versus young bone, injured bone versus a bone going through rehabilitation. What happens to a tendon and the ligament as you get older, for example. Okay, so hang on. We'll be back in just a second. Okay, if stress is basically a cause of a change in shape, like a load inside a material, then deformation and strain are the result of the load and the stress. So the load or the stress is the cause, the deformation or the strain is actually the effect, the result. So let's take a look at deformation and this equation. It's simply a difference in the length or width of a material. It's the change in shape. So if I stretch a rubber band, for example, from 2 inches to 6 inches, the change in shape, or delta L, is simply the difference between the final length and the initial length. So pretty straightforward. If we stretch a rubber band from 2 inches to 6 inches, and we take the difference between the two, then delta L of the deformation is equal to 4. So it's pretty straightforward. The farther we stretch or compress or bend or twist something, the greater the amount of deformation. And we've showed previously that this change in shape or deformation can be useful when we're talking about impulse and controlling or reducing the amount of impact force. So I'm trying to adjust the amount of light in here. Okay, there we go. Not exactly a Hollywood studio, so hang in there. Okay, mechanical strain is a measure of the change in shape of material under mechanical stress. So it's expressed as a fraction or percentage of the material's length or width. The reason we do this is, imagine you have a 2x4 and you have a section that's really short. You might notice it's actually hard to bend. But if you have the same material, this 2x4, which is made of pine, and it's really long, you find it's easy to bend. So the amount of bending that you can produce on the wood is actually proportional to the length. The longer it is, the easier it is to bend a certain distance. But the quality of it is really regardless of the length. So it's a way of equating the quality. If we take into account length of a material and the cross-sectional area, so that's basically like a cylinder. So if you imagine the middle of a bone is a cylinder, you kind of get the idea. So the length times the cross-sectional area gives you the volume. And that way, mechanical stress and mechanical strain, what they account for is the volume of the material. And that way we can talk about its quality when we look at material properties. So again, strain is expressed as a fraction of the length or width. It's mathematically can be shown as the amount of deformation, that's the change in shape, divided by the original length or width or size. So it's delta L divided by the initial length. And I usually express that, or the deformation, as an absolute value. So if you end up with a negative number, you're compressing a material. And if you have a positive number, it just means you're stretching it. That's really about it. This is an Instron machine right here. These are really cool. So what an Instron machine does is it squeezes or pulls or twists or bends a material until it breaks. So that's the really fun part about it, that you get to break the material. Sounds like a lot of fun. So working with Instron machines is pretty cool. They have one over in mechanical engineering here at Texas A&M. It's been used to actually look at bones that have been in simulated and I think real space flight. So pretty cool. But you can test bones, as you see here, tendons, ligaments, cartilage, steel, concrete, different types of plastics, polymers, etc. So really cool machine that can generate what we're going to see are stress strain curves. And they can tell us about the material properties, the strength, the stiffness, the toughness, or energy absorption. We can also look at things like ductility and elasticity by looking at the recoil. Strain is, again, a measure of the change in shape of a material under mechanical stress. In engineering terms, the units are actually units of deformation, believe it or not, divided by the original length. So it's like feet per feet in the English system, meters per meter in the metric system. And in civil engineering, they often use those standard units, but we don't tend to use it in biomechanics. It largely has to do with the fact that it's clinical value, and it's easier for the physician and the patient to understand something like a percentage. So that's the way we express it. Sometimes you'll see the units expressed as strain instead of a percentage. They mean exactly the same thing. 10% is equal to 10 strain. And to calculate it, we're going to take the deformation divided by the original length of width and then multiply by 100 to get a percentage. If a tennis racket is, the strings are in contact with the tennis ball, you can see a significant amount of compression. That's probably about 35% strain. You also are getting bending and tension in those strings. So those strings can bear probably about 80 to 90 pounds of tension, quite a bit. We're going to do just a quick problem. Let's say we have a knee ligament that's 53 millimeters long when it's relaxed. When the bone starts extending, it's 57 millimeters long. So what is the strain? So the strain, again, is going to be the change in shape divided by that original shape. So it's a fairly straightforward thing. We use an epsilon to represent strain. So as we stretch the knee, that knee ligament also stretches from 53 millimeters. We're using an MRI to measure this. The final length is 57 millimeters. We'll take the difference between the two, divide by 53 millimeters, multiply by 100. That's going to give us our percentage. And in this case, it's about 7.55%. A tendon or ligament can stretch 8 to 10% before they run into trouble, before they get injured and even tear or break. The next thing we're going to do is we're going to define some terms that are the material properties of tendons, ligaments, cartilages, etc., bones. And they are things like strength, stiffness, ductility, toughness. Each one of these is going to have an antonym, an opposite pair. So opposite of strong is weak. So a strong person or a strong material can bear a large load or a large stress before injury or failure or inability to complete the task. So bones, for example, in young adults are much stronger than in children. They're also stronger than in older adults. The opposite of strong is weak. Exercise training usually increases the strength of not only muscles, but tendons, ligaments, bones, and cartilage. Their mechanical strength actually increases. Another material property is elasticity. Elasticity has to do with a material that deforms, changes its shape, but bounces back into its original shape. So basically, it's a spring. So believe it or not, our healthy tendons, ligaments, cartilage, bones, muscles act as springs. They can stretch, they can bend, but they'll bounce back into their original shape. So when you run and take that 2,000 steps a mile, hopefully you won't be a lot shorter at the end of the mile than you were at the beginning of the mile. So like any type of spring, here's a bobblehead here. So that's like for Zion Williamson. There we go. Like any type of spring, it has an oscillation frequency. The stiffer the spring, the higher the spring constant, the faster the frequency. So the materials in our body are tendons, ligaments, cartilage, etc. We're seeing a couple of extraordinary feats here, mean that these materials are working in what we call the elastic region of the curve. That's the healthy region. That's where we want to be for our bones, tendons, ligaments, cartilage. Also, if you're doing pole vaulting, you want the pole itself to be in that healthy region. It can fracture or break because it's a molded material. It does have a bit of elasticity compared with most plastics, so it's a pretty good polymer. So when a material breaks, So, hey, you remember these things? CDs, whatever happened to CDs, right? Almost like records, LPs, which I heard are coming back. So if you bend or stretch one of these suckers, they're made of, I think, acetate, so it's a type of plastic. If you bend them far enough, they basically change their shape and they don't bounce back. So these are molded plastics. Plastics are materials that once they've changed their shape or a stress is put on them, you remove the stress, they stay in some kind of gnarly shape. This happens to tendons, ligaments, bones, muscles when a person is actually injured. So that's one of the things we really want to try to avoid, those big injuries. So the opposite of elastic for a solid is plastic. The opposite of elastic for a liquid is actually viscous. So viscous materials actually flow and dissipate energy. Plastic materials are not very good at storing energy. So you end up with a deformed piece of tissue and that can happen with a tendon or a ligament when they have a second-class sprain or strain. So that means they've been stretched so far that they don't come back. This often happens to ligaments in the lateral or outside part of the ankle, and they get in that plastic region. That means you're going to need some rehabilitation to get them back up to 100%. So silly putty is a great example of a plastic material. You pull it, or sometimes chewing gum, you pull it, especially slowly, and then it stays in that shape. It doesn't bounce back. Tupperware, if you put Tupperware in a conventional oven, turn up to 350, leave it for about 15 minutes, what you'll see is it will gnarl up and change its shape. Even when it cools, it doesn't bounce back into its original shape. So that's plastic. It's one of the reasons I don't like the word plasticity, because plastics are stuck. That's one of the reasons we actually use them. Like you can pour them in a mold and then you polymerize them either with heat stress, free radicals, or oxidative stress, pressure, etc. And then once they polymerize, then they're stuck. So it means they're pretty good PVC pipe that you can put underneath your sink because they don't change their shape like copper used to. Copper is really hard to work with. So when we have a severe injury like to the ACL, it often goes from elastic to being plastic. And that means we either need to replace it or we need to go through really good rehabilitation to get it back up to 100% again. Okay, the next set of material properties, stiff versus pliable. So a stiff material is really hard. It's difficult to change its shape, like this golf ball or a bone. They're really stiff materials, don't want to bend or stretch or compress. They will, but not very much. It takes a titanium wood going about 110 miles an hour to put like about 35% compression on this golf ball. The opposite of a stiff material is a pliable material. We do quantify stiffness in a way, so we take the ratio of the stress to strain. And that means the greater the amount of stress it takes to cause a certain amount of strain, the stiffer the material is. So you can put a lot of force on a material, but it's not going to compress very much. So it's a stiff material. Material that's pliable, like this drink plastic, is pretty easy to compress. Same thing is true with this old tennis ball. Pretty easy to compress and change its shape. So that's a pliable material. So if we looked at the stress strain curve, the slope of the curve would be pretty steep for a stiff material and flat for a pliable material. So stiff materials would be like steel, for example, bone, as I mentioned, this tennis ball, clay, etc. Silly putty, very good examples. Another material property that's not the same as stiffness and pliable is ductility versus brittle. A ductile material can bend or stretch a long way before it breaks. So steel is like that. That's why it's used as a building material. Not only is it strong and it's stiff like a bone is, but it's also incredibly ductile. You can bend or stretch it a long way before it actually breaks. So Superman is bending steel. He's the man of steel, bending steel, but that steel material doesn't break completely. It's a very tough material, but it's also very ductile, meaning that it bends or stretches a long way before it breaks. So the material undergoes a lot of deformation before failure. Muscles can actually stretch 30–40% before you start running into some problems. A brittle material is a tendency to break with only a small amount of deformation or strain, like a dead tree branch or bones in the elderly. Glass, of course, is a great example of a brittle material. Glass, believe it or not, is actually incredibly stiff. It's really strong, but it's not a good building material because it's not very ductile. It's incredibly brittle, and that means in the end it's not very tough. It can't store a lot of energy. So it's not a good building material, but looks cool. Most of the time we see it in very thin sheets. Glass, by the way, is actually a slow-moving liquid. So if you are in an older building and you look at a window and it looks kind of wavy, that's because the glass has flowed over time towards the bottom of the window. So the next thing we're going to look at, in fact, probably the last thing we're going to look at today, are stress-strain curves. And stress-strain curves tell us about the change that happens when we put a load or stress on a material. The more stress we put on, the greater the amount of strain. If there's not a lot of strain, then the material is probably stiff. As we continue on this curve and put more and more stress, it tends to change. There's literally a bend in the curve at what we call the yield point, where things are starting to give way. And we're undergoing a transition from a elastic material, which is a healthy material in a tendon, ligament, or bone, to a plastic material, which means it's been injured, especially if it's a bone, tendon, ligament, cartilage, or muscle. So we want the materials, whether they're prosthetic devices or the PCL, posterior cruciate ligament, to be elastic for as long as we can. So to test these types of material properties, we have, again, the Instron machine, where you get to break stuff, whether it's steel or concrete or polymers or a bone or a tendon or a ligament. So here we see a specimen. This one looks like it's going to extend and stretch this material until it breaks. You can even test bowling balls. You can test all kinds of things with the Instron machine. Really, really cool thing. I'm going to adjust a little bit here. Here we go. Try to get all the slide in here. Let's get a little funky on me. There we go. Okay, that's getting weird. Okay, that's good enough. It's hard to get these things perfect. All right, so stress-strain curves and load deformation curves are ways we can measure and talk about material properties. What they're going to allow us to do is make some comparisons so we can talk about the effects of aging, injuries, rehabilitation, immobilization, the effect of exercise training, either as a preventative measure to actually strengthen bones and tendons and ligaments and prevent orthopedic or sports medicine related injuries, or during rehabilitation where we're trying to reattain our material properties. And that's really what we're trying to do. So we're going to look at two different types of curves. Low deformation curves take into account quality and the size. So here size becomes important. So in instance where this would be the case, where they're designing, for example, child safety seats in an automobile, because what affects the child is the absolute magnitude of the load. It's not actually the amount of stress on the child or stress on the safety seat. It's actually the load itself. So what they're designed to do is, in our impulse equation, increase delta T. And if we increase delta T, then, as you know, force is reduced because we have an inverse relationship between the two. Stress-strain curves tell us about quality only. So that's the cool thing. We've got stress on that y-axis, strain on the x-axis. This type of stress-strain curve, by the way, is typical of what we might see for a tendon or a ligament. So we have something called a toe region where the collagen fibers are straightening out. And then we have this long, elastic, linear region. Then you see this bend in the curve. That's the yield point where things are giving way. So for a ligament, we might have a mild or a class 1 sprain before the yield point. After the yield point, between that and this final point right here, this is the plastic region of the curve. So things are literally breaking down. They're breaking down and we're tearing more fibers. So this would be a class 2 or a quote unquote moderate sprain, or a partial tear of a ligament. The final part of this curve where it ends is called the failure point. That means it completely falls apart. So stress and strain curves, because strain is basically meters per meter and stress is newtons per meter squared, we're taking into account cross-sectional area and then length. So again, like a cylinder, we're taking into account the volume of the material. So we can fairly compare small and large bones and talk about the quality. So in the curve, we have, as I mentioned, an elastic material where a bone, tendon, ligament, cartilage will return to its original shape when we're running, walking, playing tennis, volleyball, etc. A yield point where the material starts to give way, that bending point that we looked at. A plastic region where the curve kind of flattens out. And then finally, the failure point, that's the end of the road. That's where we get complete damage and separation. So that would be a class 3 sprain or a tear of like the ACL or PCL. So with stress strain curves, this would be one we would see for a bone, for example. The slope of the line in the elastic region determines the stiffness. So stiffness, remember, is the amount of stress divided by the amount of strain. When you have a curve like this, the change in the y-axis divided by the change in the x-axis is equal to the slope of the line. The steeper the slope, the stiffer the material is. Then we have a bending point or yield point where the material starts to give way. So this bone goes into a plastic region. This would be a partial fracture, like a green stick fracture. Then a failure point would be a simple or a compound full fracture. We obviously want to avoid that. So again, the slope of this line is the change in the y variable divided by the change in the x variable. Since the y variable is the strain and the x variable, the y variable is the stress and the x variable is the strain. When we put those together, we get a change in stress divided by a change in strain. That's the stiffness of the material. It also has a name called Young's modulus. The stiffer the material is, the steeper the slope. The stiffer the material is, the steeper the slope. So for example, I have two bones. We have maybe Amy and Betty. So with Amy, when we look at the slope of the line, it's clearly steeper. So there's a greater amount of change in stress for a given change in strain. So it takes more stress to basically bend it or stretch it or compress the bone. For our bone here, we've got a flatter slope, and that means that for this individual, what we have is a bone that's not as stiff. It also turns out to be not as strong as well. This might be the bone from a child, like a 10-year-old child, for example. When we look at a stress-strain curve, the peak stress or peak load that can be taken before it breaks is the strength. So the stronger material is, the more stress it can take before it breaks down. And on a stress-strain curve, it's just wherever the peak is. And so the Instron machine, once we go through a stress-strain curve and either we're stretching it or compressing it or bending the material until it breaks, it's whatever that peak value would be. That would be the strength of the material. And it's often, but not always, pretty near that yield point. Sometimes with bones, it's a little bit farther along. Right when we're getting to the yield point, that's the end of the elastic region. This is, again, is the healthy region of, say, a ligament or a tendon. We might have a mild injury near the end of the elastic region where things are starting to give way. So we're tearing a few fibers, and maybe some blood vessels, but not enough so there's a compromise in the mechanical integrity. It's still that the tendon or ligament would still have its strength, stiffness, its normal mechanical or material properties. Once you get past the yield point, then you go from being elastic, that's this part of the region, to plastic. That's where we get an injury occurring. And the failure point would be the worst type of injury, complete fracture. So we go from mild to moderate to severe in our stress strain curve. Okay. So a moderate injury like a green stick fracture or a moderate sprain occurs in that plastic region. That's past the yield point, whether it's a tendon, ligament, or bone. A failure point, that means the material is completely broken. If it's a muscle, it's a complete tear. If it's an anterior cruciate ligament, it's a tear or a class 3 sprain. If it's a tendon, this is a tear or a class 3 strain with a T. If it's a bone, it's a complete fracture. It could be simple or it could be compound. End of the road. Another material property we talked about was ductility versus brittleness. Ductility is measured as the amount of strain something can take before it breaks. So with glass, for example, glass actually has a very steep slope. It's stiff. It's actually pretty strong, but it breaks with only a little bit of strain. So that means the ductility is very low. The strain to failure point is very, very low. So we're comparing two bones again. Amy and, I forgot who B was, Bethany. I'm going to make it Bethany, even though I don't think that's right. Amy and Bethany. So Amy is maybe a 22-year-old, someone about your age, and their bones are stiff. If we look at the peak stress, they're pretty strong as well. But we look at ductility, and that's the amount of strain before the failure point. You can see with Bethany that her bone actually has greater ductility. It's not as brittle as Amy's. So the chances of a fracture are actually higher because the bone's not as stiff, it's not as strong, it's not as tough, but it is more ductile. So what that means is that when Bethany has a fracture, and she's probably maybe a 10-year-old kid, it's going to be a green stick fracture, a partial fracture. So that's the good news. They recover pretty fast. So the area under the curve, we were looking at this a second ago. The area under the curve is actually the toughness. This is the total amount of energy that the material can store before it fails. It's technically the integral of stress times the strain. It's the combination of stress times strain, or you can say the product of stress times strain. So in calculus, we would take the area under the curve. That's the energy that can be absorbed. We call that the toughness. The greater the energy of the area under the curve, the tougher the material is. The amount of energy a bone or tendon or ligament can store up to the yield point, which means you stay in the plastic healthy region. So this would be something like a super ball, which never seems to break. That's what we call resilient. It means that that material, including a bone or tendon or ligament, is not likely to be injured at all. So that's actually great news. That's exactly what we were looking for. So Amy and Bethany again, if we look at the area under the curve, I'm going to go and look at the total curve. For Bethany, it's not nearly as large as it is for Amy, even though her bones are more ductile. So that means the chance of a fracture are higher. That's not surprising because Bethany's bones are mostly ossified cartilage. They're softer, they're not as stiff, they're not as strong, but when you stretch them or bend them, they'll go a little farther before they actually break. So a partial fracture, a green stick fracture for her is going to be a lot more common. So a few terms, some of which we've mentioned. Elastic, remember, that's like a spring. That's the amount of bounce something has before it returns to its original shape. The opposite of elastic is plastic for a solid, viscous for a liquid. So for muscles and cartilage, for example, we usually use the term viscous. So a viscous material is thick, it flows slowly, it dissipates energy. So motor oil, Slick 50, molasses. Those are all examples of viscous materials that dissipate energy. So that's why motor oil works really well in your gas or your diesel engine, because what they do is they dissipate the heat, get rid of it, keep it away from your piston so it doesn't crack. Viscoelastic is a combination of viscous and elastic. So we actually see this when we have a material, for example. If it's stretched rapidly, it's elastic, like a rubber band. If it's stretched slowly, then it becomes viscous. Skeletal muscle is like this. We stretch skeletal muscle fast, like with a wind-up, it's elastic. If we stretch it slowly, let's say that we're going to do some flexibility exercises, then it actually becomes viscous. Viscoelastic materials undergo something called hysteresis. It means they lose a lot of energy when the load is lifted. Your lungs are like this. When you breathe in, they're elastic, and so is the chest wall. When you breathe out, you actually want to dissipate energy so it doesn't squeeze on your bronchioles and alveoli and reduce the amount of air that could be expended. So when people have, for example, asthma, it happens because the smooth muscle in the bronchioles constricts or contracts. And even though they seem to have trouble breathing in, the real problem they have is breathing out, because they can't breathe out fast enough, especially if they're exerting themselves. Then they're trying to breathe in before their body's ready. So we want actually the lungs to be viscoelastic. Skeletal muscles are kind of viscoelastic. So the way we look at that, we can even quantify that. If we have a low deformation curve or a stress strain curve, it's the difference in the slope and the curve between when it's loading versus unloading. So lungs will do this. You breathe in and then relax on the way out. It's one of the reasons you want to relax, because you don't want the expiration to be elastic. You want it actually to be viscous and, believe it or not, dissipate some energy. So breathe in and then relax and breathe out. So do some breathing exercises, just relax. And that's going to do it pretty much for this week. Lecture. One last term I'm going to define, and then next week we're going to come back. We're going to talk about how cells detect mechanical stress and strain so they can make decisions on how much protein to produce, like collagen and myosin and actin, depending upon whether it's a bone or tendon or ligament. The last term we're going to talk about is a cool one. It's called creep. It means that when you have a material under a constant load, it changes its shape over time. So this is sometimes used in casting to try to reshape limbs. I've got, let's see, here we go. We often use this for fractures, but sometimes people will use this to reshape a limb or a hand or a wrist, especially when there's a severe injury. So here's a soft cast, for example. So creep means there is a certain amount of strain over time under a constant force or load. Another example, believe it or not, has to do with your vertebrae during the course of the day, especially if you're standing a lot or even sitting a lot. So over the course of the day, there's a constant load on your vertebral discs. They actually flatten out over time because water tends to escape them if the loading is fairly constant. If you're running and the loading is kind of up and down, then what actually happens is the cartilage is more elastic. It flattens, then it bounces back, flattens, and it bounces back. But if you can imagine you're at Buckingham Palace and you are a guard, you're standing for a long time. Your vertebral disc will actually flatten out over time as water actually escapes from it. During the course of the day, most people are about 1/8 to 1/4 of an inch shorter at the end of the day than the beginning of the day. So if you want to look tall, measure your height at the beginning of the day. They try to wake up the basketball players to do that, especially if they think they got a 7-footer. Want to measure that 7-footer at 8 a.m., not 8 p.m., because they could be 6'11" at 8 p.m. Okay, that's it. We probably ran a little bit long. I got to actually get a timer, so I know how long these things are going. That's it for this week, and we'll see you again next week. we do have, as I mentioned before, we are going to have, I think, hopefully, a quiz coming up on Friday, and we're going to have a question and answer session on Friday as well. So mechanotransduction next week, and maybe we'll start skeletal muscle mechanics. So thanks a lot for listening and hanging in there. Hope you guys are well, your families are well, and we will see you guys soon. Thanks very much. Have a